Good morning, everyone. I'm Manuel Matteo from DG Connect here at the European Commission, speaking to you live from my home in rainy Brussels, where summer is only a word in the calendar, and in the name of today's Connect University School. This Connect University was established in 2015, and it's the knowledge sharing flagship initiative of the European Commission's Directorate General Connect, which stands for Communication Networks, Content and Technology. We aim to inform the public about the latest digital trends. So we place cutting-edge technologies high on the political agenda, and we try to present, explain to you how we work and where we find inspiration, where we identify current opportunities and threats as well. And we try to build synergies, therefore, in between institutions, industry, academia, but as well international organizations. This project of Connect University is really a trademark for debates and policy advice. We raise awareness about ongoing digital revolution, and we prepare more broadly the society for future changes. This year's edition of the Connect University is focused on digital for our planet. This is the focus of this year. We are trying to address the way digital technologies are harnessed to tackle climate change, both in terms of a greener digital system itself, which will be rather the focus of today, but as well the focus in the role in helping reducing carbon emissions across industries and society. All the sessions are recorded and will be reviewed and can be reviewed afterwards directly on the Digital EU YouTube channel or on the Connect University webpage. And the links are already published on Slido, and you will be able to review this session as of next week. For today's session on energy consumption of data center, you can all join, so you can all watch us on YouTube, but as well, if you want to interact with us and ask questions to the speakers, you should join us via Slido using the code, the hashtag energy. You can comment and ask us questions there, and I'll do my best to allocate them accordingly to our speakers, possibly recombining them. As well, please use hashtag Connect University when sharing insights on social media. And a final quick reminder for those of you who are following at least 7 sessions of the summer school program, we'll be giving you a diploma at the end. So without further ado, let me introduce the first of our speakers, Piers O'Donoghue. He will briefly introduce today's sessions and the subsequent speakers. Piers, the floor is yours.
Thank you, Manuel. Good morning to everybody. You're very welcome to the Connect University Summer School. The fact that this year's summer school is devoted to digital for our planet is a reflection of the fact that we need to take urgent action to achieve carbon neutrality. So even if digital, which we work on, is one of the 2 priorities of this European Commission, greening and our zero carbon goals, the Green Deal, are the other objective. And we must, in our work on digital, also ensure that we are working in the direction of a low carbon economy. Because in that context, digital is a key enabler to take action. But the ICT sector is itself energy hungry. So we need to square that circle in order to ensure that we are practicing what we preach and exploiting digital technologies to their maximum potential for the greening of the entire economy. Now, this morning's session's focus, as Manuel has said, on data centers and their energy consumption, because those data centers are really the power plants of our digital society. And the digital decade communication from the Commission re-emphasizes our commitment to making data centers climate neutral by 2030. So highly resource efficient data centers, they will be the backbone for the next generation of highly secure and sustainable European cloud and edge capacities. Now, according to our latest figures, data centers will account close to 3.2% of the EU's electricity demand by 2030. And our first speaker, Simon Hinterholzer, will provide more insights into the research behind this and other interesting findings. Because EU policy in this domain, well, it's really still in its infancy. Data centers, they're very complex, multi-layered. They come in all shapes and sizes and cater to the whole range of digital needs. But through existing initiatives, as well as new ideas, we aim to develop our policy into a long-term, sustainable approach to ensure that we achieve the objectives of the Green Deal and the digital decade, which I mentioned, which we're calling the twin transition, the digital transition and the green transition. As well as those policies, there are, of course, industry-led self-regulation initiatives, most notably the Climate Neutral Data Center Pact. And our second speaker, Emma Fryer from the Tech UK, she was instrumental in designing this pact and I'm sure will play a key role in its implementation. Now, the question we all have is, what are the right measures to put in place? And to answer it, we need solid evidence, notably data to support the policy and the corresponding indicators. And for this, we need some essentials, a definition of what to measure, what is the unit of analysis, and the most appropriate metrics to do so. Do we want indicators, a measurement framework, etc.? So DG Connect, we are ourselves conducting a study to help solve this puzzle with the results expected at the end of August. So that is something to look forward to in the short term. And then from proper metrics come informed policy actions, benchmarking, awareness raising campaigns, and exchanges of best practice. All of those can feed into related and relevant ongoing legislative or non-legislative proposals, so including soft policies and self-regulation, as I've mentioned, as well as helping to build the future initiatives. So a couple of examples of those would be our Joint Research Centres Code of Conduct for Efficient Data Centres. That's one of the foundations for future action in the field. The revision of the Energy Efficiency Directive, the eco-design regulation for computers and for servers, and then we have sustainable finance taxonomy, and finally, green public procurement criteria. So a range of actions taking different approaches to tackle the same problem. Now, on top of this, we will obviously need to mobilize the different funding mechanisms at our disposal. We have the Digital Euro program, which is a new kid on the block, but very promising for these kind of targeted deployment actions. We have, of course, our research funding under Horizon Europe. We have the CEF2, the Connecting Europe Facility funding, as well as the very large funds recently released to the member states under the Next Generation EU fund called the Resilience Funds, in order to allow economies to kickstart after the COVID crisis. But where again, we will be putting a huge emphasis on the Commission's twin priorities, the Green Deal and digital, and using digital to harness its ability to help in reaching our low carbon targets. Now, of course, it goes without saying that with all of those initiatives in mind, we will and we have to, and we are committed to continuing to engage with the whole range of stakeholders, those of you who are listening today, those who have an input for approaches, but also, of course, those who have the real expertise that we, the Commission, need to harness and to work with in order to reduce the energy consumption of data centers. So our third and last speaker is Jan Michel, who's probably the most hands-on of today's speakers. He is the CEO of a European cloud provider, and we can say that he lives the struggle for environmental performance on a daily basis, which he will tell us about. And we will be keen to hear from Jan how he does it in an innovative manner. But we have a great lineup of speakers, and I really do hope that you would then get involved in the discussion and the question and answer session afterwards. I look forward to this important session today. Thanks for your participation and best wishes to all of you.
Thank you very much, Piers, for those for this excellent introduction, to which I have nothing else to add. Simon, Piers already introduced you. You conducted a study for us that we published a year ago with a projection of data center energy demand by 2030. I understand you're going to present to us the broad lines of that study, but since it's a year old as well, a few updates and tiny changes since then. Simon, I'll verify that the microphone is fine, and then I'll leave you up to present.
Yeah, thank you, Manuel. Thank you, Piers, for that great introduction. That was a good motivation to go into that study. I'll just share my screen now. Just give it a second. Hope you can see that now. So
yes, your screen is clear now.
Okay, perfect. So first of all, hello everybody. My name is Simon Hinterholz. I'm working at the Overstating Institute in Berlin. Right now, I'm talking to you out of the home office, and I will tell you something about data center energy consumption in the European Union. As Manuel already mentioned, most of the findings are based on a study that was commissioned by DG Connect of the European Commission and published last year in November. There is also some updates from other studies, but the sources can be found in the end. I think all questions can be posted to the Slido tool, which was sent to you by the organizers. So let's start. First of all, the use of ICT is changing. We have ICT since a long time, and even that picture is already a quite advanced technology of ICT, but it's back to the 80s. It's one of the first computers from Apple. It's called Lisa, and the use of ICT is changing all the time. So we have new technologies, we have advanced technologies, we have more and more connected devices. These devices are more powerful in terms of picture resolutions, in terms of abilities of connectivity. Then we have replacement of physical things, like even currencies are going more and more digital. We see this cryptocurrencies, for example. We have applications that are not running anymore on the end user device anymore, but most of the workload is placed into the cloud. And we are getting more and more data-driven business models. So where does all of these trends lead to? These are quite intense trends, and all of them lead to more data traffic. This is just an example for mobile data traffic in Europe, based on figures from Ericsson. And we also have that in the fixed networks, but this is for wireless networks. And we also have more workloads in data centers, and there are very different types of data centers. We have more public clouds and private clouds, and we have high performance computing data centers that are more for research or more for specific purpose. And so this whole field is quite heterogeneous, and we need to look very close to get an idea what all of these trends are doing there, how our devices are changing, how they are getting more and more. And this is quite a difficult task to do. And also the quite abstract name of the cloud, which is the name for actually huge infrastructures that grew over more than the last 10 years, and it's just a special type of data centers that have some fundamental characteristics, like elastic computing, where you can just use resources when you need it and you don't use it if they are not needed. They're getting also bigger, so we see, like in the last years, really huge data centers that are coming at the scales of warehouses. from thousands to even 100,000 of square meters of IT space or just IT equipment is placed, where there is additional rooms for cooling equipment and other things. And yeah, we see data centers in the range of 100,000 square meters, which is just to compare that a hectare of land, if you know that from agriculture, that's 10,000 of square meters. So 100,000 is like 10 times one of a hectare. So it's getting quite big, and what we see is growing. Like the growth in that sector is quite intense in the last years. So yeah, we need to look closer what resources are used to build all this up. So even though this cloud paradigm, which was established like more than 10 years ago, is bringing us a lot of opportunities to transform the traditional way we are using data centers into a more shared multi-tenant infrastructure where service or network equipment can be shared among different applications. So if you're using some service, for example, for email during the day for the office, these servers can be used at night for maybe video streaming or gaming or other purposes. So you have huge efficiency gains by not placing every server for every application, but it also brings us a lot of growth. So to get deeper into that, here's just a picture of a small one. This is a research data center of CERN in Switzerland. Let's go into some findings of a recent study which we've done for the European Commission for DG Connect. And first of all, there is a lot of different results on energy consumption in data centers worldwide. This comes because there is only actually few data available on the actual amount of servers that is out there and how these servers are looking, but there are also quite different modeling techniques how to calculate the energy consumption of data centers. So different researchers have different projections, and some of them also have very like long-term extrapolations of trends of just like 2010 or 11, extrapolating them to 2025 or 2030, which is, if you know, like exponential functions. I think all of us got to know them in the pandemic recently. If you try to extrapolate them, you have high insecurity of like the accuracy of the extrapolation, because depending on what you estimate behind the growth, the results can be very different. So just to show you some studies, we have these studies that are going really high in 2030, and but they also have a high range between their like expected maximum outcome. And Andre, for example, corrected his studies from 2015 and 2019 to change that his exponential function to a much lower value in his expected scenario. And there is also the current situation for data center energy consumption, where we have, for example, Eric Mazanet and his team of the US publishing results here, also with a bottom-up model, which is quite similar to the model we use, but they have a bit different assumptions and a bit different definition of data centers. So they come to lower results of global data center energy consumption here in 2018 and 2020, which is published by the International Energy Agency, but it's also based on the results of Eric Mazanet and his team. So we have different projections with different results of the current situation. So this is a quite difficult topic, and we actually have not that much data available. So I'll just give you a short insight into our modeling approach and our results, which we have used for the study on energy-efficient cloud computing technologies and policies for an eco-friendly cloud market. I mentioned that before. We did that for DG Connect of the European Commission. We carried out the study from December 2018 until May 2020. And there were some validation workshops in Brussels with stakeholders, also to discuss some policy measures that can be done on top of that results. We have created some modeling where we see on the base some physical layers where we have some networks at the fundamental base, where we have this different type of backbone, internet backbone, and the access networks, but we also have the different types of storage and compute capacities at the edge, at corporate data centers, at co-location data centers, but also the big hyperscale data centers, which are operated by cloud providers, public cloud providers, and those big IT companies. On top of that, we see a lot of software layers, which is mainly based for the cloud environment on virtualization on the bottom, virtualization technology, hypervisors. Then we have operating system and middleware, but also in the end, the application software and the data, of course. And out of it, we get software, we get platforms, and we get infrastructure services from these cloud environments. And what we put into, and at the bottom, at the physical layers, is energy. So if we talk about efficiency, is we basically want to get out a lot of these outputs by putting in less of energy. Like, this is just the definition of energy efficiency in cloud computing, how we understand it. For the modeling of the energy consumption, I will not go too deep into that model, but just to have a quick understanding how we did this is mainly we try to get a lot of information on how much service, storage, and network equipment has been sold in recent years, so we can get an idea how much is out there and running right now. We have done a lot of research with the industry. We have done studies and surveys about the energy consumption of these individual equipment. We've seen a lot of literature, other research institutions to publish about some general ICT technology trends. How much are these individual components are consuming, and how these components are utilized. Like, is this server just running at a few hours per day, or is it running all day long, all night long? So it consumes a bit more energy, of course. And so we can calculate the energy consumption per year, and we can add up the infrastructure consumption for cooling and for light and for the power supply. You know, these data centers are have a quite secure power supply, which has a high quality of supply with batteries, and so we can calculate the energy consumption of data centers for every year if we do that for many years, so we can get a timeline. And what we get out of that is the energy consumption of data centers for the European Union 28. So that study was done or commissioned when Great Britain was still in the European Union. So we have the EU 28 here, where we have calculated 78 terawatt hours of energy consumption for data centers in the European Union, which has increased from about 54 terawatt hours. And you see the strongest growth has happened in these bottom categories, which is the ICT category, service, storage, and network. And so the ratio between these IT equipment to the infrastructure consumption is getting a bit higher. So we have more energy consumed by these IT equipment, which comes with the better. There is a metric called PUE, power usage effectiveness, that rates the power that is used by the infrastructure compared to the power that is used by the IT equipment compared to the complete energy consumption of the whole data centers. So that has increased from 2.03 to 1.75. So the efficiency has increased slowly, but yeah, there have been some improvements, and yeah, we also see them for the future still improving. And with the forecast from every number here beyond 2018 is forecasted already, because when we modeled that in 2019, the latest figures we could get was for 2018. What we see here is the energy consumption is still increasing. It's a bit slowing down probably in the mid-20s, but yeah, the amount of cloud, or the share of cloud data centers, is increasing much faster, and traditional data centers, which are just like on-premise corporate data centers, for example, you have a specific server for your own email services, will not or will be reduced for the future. And we are seeing another category of data centers rising, which we call the edge data centers. Edge is a term that is not very well defined yet, but it has, according to the to some other research, we consider that as getting the last miles to the customers or to the end user devices. So we have more distributed data centers that are getting smaller, and we get a lot of compute capacity into there because we have new applications that need these low latency. This is the signal running time between the data center and your device for specific applications like autonomous vehicles. We have some AI applications or on-demand cloud gaming. So that will be provided, that applications more and more from edge data centers. And they can play a role from 10% probably in 2025, we expect. 10% of the compute capacity, but about 12% of the energy consumption, because smaller data centers often are not as efficient as huge cloud data centers, which are really optimized in many cases and have more opportunities to optimize their energy. So about the CO2 emission, this figure is from a different study we also published in 2020. The sources can be found in the end, where we already see a decline in CO2 emission slowly, which comes due to the replacement of fossil fuels in the electricity sector. We have not considered the individual electricity consumption of single data center operators, because there are many who choose green power for supply. We just use the average emissions of the national grids according to the EUCUS scenario by the European Commission, which has a projection until 2030. But especially in Western Europe, the emissions will remain quite high because we have still a strong growth in data centers, and on the other hand, we still have a lot of coal power that is fading out quite slow. I think this whole projections are being overthinked now because we have new ambitions, new goals set for 2030. So this can be improved, of course, by policy still by a lot. But that is the current estimation based on the recent projections of carbon emissions of the power sector. The important trends or most important factors for data center consumption for the future. Of course, we all know that all of our devices are getting more powerful. The chips are getting much more computing capacity. We have more storage capacity in our devices. This comes all with Moore's law because of the miniaturization of ICT equipment in chips. And this helped also to increase the amount of computation per watt energy consumed, or the amount of storage per watt or per energy unit. So this helped us a lot in the past to increase the energy efficiency. There is derived from that Moore's law, and combined with the Dennard scaling is the Kumi's law, which is coming from Jonathan Kumi, a researcher from the US who did a lot of research about ICT energy efficiency in the past. And he also said, in the past, the energy consumption per watt has being halved every 18 months. So we have a constant improvement of energy efficiency, if you want so. But still, those chips typically use always the same amount of energy, or they even are slightly increasing their energy consumption, even though they have multiplied the power of output capacity, of computing capacity, of storage capacity So the term energy efficiency, if you remember, the output has increased heavily. The input also might have increased a little, but like compared to the output, the input has increased much slower. So this is an overall increase in energy efficiency, definitely. But what we see here is also that the server energy consumption, if we look at device level, we have a huge range of different servers, and you can see the power consumption of servers, the rated power of various servers that have done the spec power benchmark, which is and published their results online. We see an increasing trend in the power consumption per server here, which is just one data source, which is not representative for the whole server market, of course, but this is one quite interesting trend that we are watching, that servers tend to increase their average energy consumption per device, like per physical unit of server, the energy consumption is getting bigger. So we have a lot of important trends like immersion cooling. Here you can see these ICT equipment that is just put under water, but it's not water. It's of course a specific liquid that is not has a high electric resistance, so that you don't get short circuits, which helps you to get cooling your equipment without like pumping a lot of air through it, which also consumes a lot of energy, and getting away the heat more easily through the liquid. We also have a lot of new CPU chip technologies, but we are getting problems maybe with the Moore's law in the long term. There are still like some problems occurring in the miniaturization of components, but this is very hard to predict where this is going. And we also see a lot of potential with waste heat utilization and of course, if we look at CO2 emissions with renewable power for data centers, and there is this concept of carbon-aware computing where we put the workloads there where the sun shines, where the wind blows, that also helps to reduce grid bottlenecks and reduce storage capacities that are needed for a 100% carbon-free electricity supply. So the trends, the future outlook is quite hard to do. You can see that there's different lines to the 2030, depending on what policy decides where we should go. We have ambitious goal for climate neutral data centers for 2030. I really like that high ambition of the European Union here, and we can also reduce the energy consumption of data centers if we get ambitious here. Here are just some literature, the sources I've mentioned before, and I say thank you, and maybe there is 1 or 2 minutes for questions now left over.
Thank you, Simon. Thank you very much. I really felt like sitting on the benches of my university. We have 4 or 5 minutes for a few questions, and there were many. So what I suggest is that you answer each of them with one sentence, and
okay.
Rather pointing people to the answer rather than developing too much. The first question comes from Lionel, who asks whether there's an established difference in definition between a data center and a server room.
Well, this is a very good question, because that describes some difficulties in modeling, and actually there is not an we do differentiate if we model that. Like we have these server rooms which don't, like there are small server rooms that don't use cooling at all. They just open the window, and then there's more advanced server rooms, and there is big data centers, of course. And I think in the data center definition EN 5600 there is some differentiation between these data centers, but I think, yeah. So for us, we differentiate in modeling the energy consumption between small like server rooms and big data centers. For us, this plays a huge role, but in the reality, of course, there is the change between small rooms and bigger rooms are just fluid. Like there is no hard line. This is a data center, this is a server room.
Thanks a lot. Question on two technologies. The first one is from Elder, who asks whether the impact of decentralized data storage systems such as Filecoin, whether you know it, and a different technology, Maciek is asking about the impact of quantum computing. Complicated to answer in one sentence. Okay, yeah. The first, if I understood this right, is distributed data storage, where we have that already. It's called like content delivery networks in the internet, and it's helping to reduce the network traffic on the transmission lines on the long ways. So that helps to reduce the energy consumption on the networks, of course, and it can improve energy efficiency on the network side. But of course, there are added some equipment and at the edges, and this has to be considered individually. But it has some potential, of course, to reduce energy consumption overall. And the second one, quantum computing, is of course a very interesting technology, because in some cases, in some specific cases, it can help us to reduce computing capacity of traditional servers by a lot, which is very hard to compute by traditional servers. So this is like it goes into the like thousands, like factors of thousands are in between those, which is used in capacity. But on the other side, of course, these quantum computers, at this time, these quantum computers we have right now need to be cooled almost at the absolute 0 degree Kelvin, which is about minus 273 degrees Celsius. And this cooling infrastructure, of course, needs a lot of electricity as well. But there can be also chances in that. So right now it's quite hard to predict if it's an overall win. It will definitely add something to the infrastructure we have already. It will not replace them. So we will probably have some additional energy consumption, but maybe it can replace some parts of it. But yeah, it's also hard to answer if that has a net benefit or net negative effect. Thanks a lot, Simon. The two final questions really on your modeling. Natasha is asking, what is the, I'm simplifying, but what is the one data that you are missing to improve your model? What is the one that would make a difference into the quality of your modeling? And Nicholas is asking what has been the energy efficiency gain or not over the last 10 years?
The most important data is the actual energy consumption, which is of specific data centers, which is already like measured in the data centers. The operators, they have them, but they don't want to share them because it's a business secret, and they have good rights for not sharing them. But for us, this of course would help us a lot. And so we get some information from data center operators because they trust us. We are some non-profit organization in the middle, so they trust us that we not publish their individual results. We just add them up with others, so they are more anonymous in there. But we include these figures. So if you have some information, just tell us or just send it to us, or get in contact. And what was the other question?
What has been the outlook of energy efficiency over the last 10 years? Have we improved, or is it stable, or did it get worse?
In terms of energy efficiency, we have improved hugely. Like we have improved at a factor of 10 probably over the last 10 years, or even more if we depending on if we consider compute capacity or storage capacity or network capacity. This might have even increased at a factor of 20. But so in terms of energy efficiency, we have improved a lot, but in terms of absolute energy consumption, we have increased still. So this is important to distinguish between energy efficiency and total amount of energy consumption.
Thank you, Simon, and we'll leave you there with this very final and important distinction there. Thank you, Professor Simon. I think you've earned your title. Emma, you're next on the stage. You're done a mixture of many things, always around data centers. You've negotiated the climate change agreement for the whole sector in the UK, but you've dealt as well with key worker status, production of construction sites during COVID as well. And from the times we've discussed, you and I know that you are extremely knowledgeable on everything that goes into the sector. So the floor is yours for 20 minutes. And to the public, let me tell you that it's easier for me to collect questions as the speakers speak than afterwards. Thanks a lot, and the floor is yours, Emma.
Okay. Right, so yes, thank you so much. That's a very kind introduction. So I'm Emma Fryer, and yes, I've been looking after the UK data centre sector for about 10 years now. So I've had it's a very large sector, I think the largest in Europe. So we've had a lot of discussion with policymakers both in the UK and Europe. And there's a great segue actually from Simon's presentation. We do in the UK measure data centre energy consumption, but we don't measure all of it. So it's a bit like the old Donald Rumsfeld thing. There are known knowns, there are known unknowns, and there are unknown unknowns. Our known knowns is the commercial sector, which we measure down to the kilowatt hour. So really happy to share all that information with Simon. It's publicly available. And actually our last figure is 3.6 terawatt hours for the whole of the commercial sector in 2020, which is about 1% of the UK's electricity demand. But that isn't the whole picture, and we're going to come on to that in a minute. Right. Where I was going to start was, what is a data centre? And I know we all know that, but just to remind us, it's where the internet lives. By internet, I don't just mean pictures of cats. We mean everything that's digitally enabled. So it's transport, supermarket logistics, government services, medical research, modelling, monitoring. It's a huge list. And obviously, as Simon referred to, there are different types of data centres. We've got enterprise, which are the on-premise in-house. We call them enterprise. I'm not quite sure why. And that includes your server rooms. And there's a real tension in whether we define a server room as a data center. We in the commercial sector don't, but lots of people do. And that's one of the reasons we see variations in the estimates, as Simon referred to. Then we have those that provide outsourced services, co-location, where other people stick their servers in. And the co-location provider essentially provides the infrastructure. And then obviously we've got the hyperscale, and now we're seeing edge as well. There's obviously some blending. And then I think it's worth mentioning how much we realized we depended on data centers in the last 18 months. And that was one of the reasons that we had to negotiate key worker status for people working in data centers last year with the UK government. And I have to say they responded really well. So just have a look at data center energy use. I think it's worth us quickly, briefly looking at this. And I've got this is the ICT stats from Ericsson in 2018. And the IEA think that data centers consume about 1% of global electricity, which is around 200 terawatt hours a year. I don't think that seems to be broadly in line with what Simon's saying. And studies suggest that data centers are consuming between about 15% and 25% of the overall ICT energy. They have a lower proportion of embedded energy, and that's because everything in a data center works 24/7, as opposed to something like a mobile phone, where there's a much higher proportion of embedded energy in the device compared to its use phase energy consumption. I think I've mentioned that we use 3.6 terawatt hours in the UK, but I think we also just need to plant that fact that they are electro-intensive. Then I wanted to talk a little bit about growth. And this again has been referred to by my colleagues on the call. This growth curve shows the London co-location market. So London commercial providers, we use megawatt hours of power provisioning as a proxy. That doesn't equate to power consumption. Just need to make that clear. But you'll have seen that there's a consistent growth in this market over the last, actually 13 years, I think we've got there. So we're electro-intensive and we're growing. Obviously, we all know what's driving the growth: digitization, digitally enabled government policies, the migration and outsourcing of on-premises data centers, very important one I'm going to come back to later, and the consolidation and outsourcing of what we call distributed IT, which is sort of servers sitting around in offices under desks and in little cupboards, even below the level of a server room. And then, of course, there will be development and adoption of new data-hungry technologies. And increasingly that's being delivered through cloud. So as I said, we're electro-intensive and we're growing. So that presents the conundrum that we've just been discussing. So how are we doing? As Simon referred to, we have this ability to continue to deliver more capacity without a concomitant increase in energy demand. So these figures are from the International Energy Agency. The top pale blue line shows internet traffic. The dark blue line shows workloads in data centers. And then the bottom green line, which does look remarkably flat, I would have nudged it up a tiny bit, is data center energy use. So this is the big conundrum for us. We've got to meet the exploding demand for digital data without data centers suddenly gobbling up more power. So we've all got to live in caves and eat bugs. So as Simon said, processor efficiency and advances like virtualization. But I was surprised to see that line so flat because we see so much development, particularly at the hyperscale end, with large electro-hungry plants going in. So I'm going to look under the bonnet. And again, this is really a version of a slide Simon's already shown. This is essentially representing what's happening in terms of migration. So we're looking at a dramatic growth in hyperscale, which is very visible to everyone. We're seeing those sites being built. We're seeing them go through planning. We're seeing how big they are. And then we've got growth in cloud, but we've also got, at the same time, a massive decline in that traditional on-premise. And what you have to bear in mind there is that when you run traditional distributed IT, it's probably several orders of magnitude less efficient than a cloud alternative. So that gives us quite a bit of headroom. Won't last forever, but it does give us a fair amount of headroom. The problem with the traditional is it's not visible. We don't actually know how much there is. So the latest figures I've seen suggest that about 50% of activity is still on premises. So that means there's actually more headroom in that pale blue traditional area that's declining than perhaps we'd thought. But we just don't know because nobody reports it. We've got no transparency on that whatsoever. What we do know, and there's some great stats from the Eureka project that I can share with you if needed, we do know that that's generally pretty inefficient. So it's great to see that declining. So this is really, this is talking about, just backing up again, another slide that Simon showed, but this one's actually, it's really a proxy, but it's showing, it's a logarithmic scale for essentially the the energy intensity of the fixed network. And this you could actually apply to data processing because roughly the same chart applies. And actually over the last 3 decades, in terms of data processing, the amount of energy required to process a given amount of data has reduced by about 6 to 7 orders of magnitude. So last 3 decades, 6 to 7 orders of magnitude, it's the amount of energy required to process a given amount of data, which is pretty impressive. If you applied that to aviation, which is a really bad comparison, so don't, but if you applied to aviation, you'd be able to fly a jumbo jet to New York from Europe on about 3 teaspoons full of fuel. There are many reasons why that's a bad analogy, as I've been told frequently, but it just shows you just the incredible increase in efficiency. So that's that. Right, then we've got this problem of price elasticity. And I did want to bring this up because this is the really important thing, again, that both Simon and Manuel have referred to, that yes, we're getting more efficient, but we're using overall more power. And this is about the difference between a price elastic and a price inelastic commodity. Communications are incredibly price elastic. The less you have to pay, the more you do it. And that compares, I've chosen coffins. Coffins are really price inelastic. You know, I'm only planning to make use of 1 coffin. And if coffins become less expensive, I'm not expecting to stockpile coffins. Or if they become more expensive, I'm still going to have to buy one. So a coffin is a really price inelastic commodity. And some great work was done, actually, I think 2 centuries ago by Jevons, who explained this, that as you reduce the price for something, the demand can increase so much that actually you use overall more energy. I'm simplifying that, but do have a look at Jevons paradox. It's put up all over. You can find it on Wikipedia. I think that's the same picture because I think I've pinched it from there. So just be aware of this price elasticity issue. And then I did want to mention streaming because it's very, very topical at the moment. We've just had a really interesting study from the Carbon Trust in the UK, which reckons that on average video streaming emits 55 grams of carbon dioxide per hour. But the interesting things that came out of that study are that the largest part of the footprint is attributable to the viewing device. And I think they say that if you watch it on a 50, I don't know what 50, I'm talking in inches, but say a screen that is about a meter, a TV screen that's a meter wide, that uses 90 times as much power as watching it on a smartphone. So that's the biggest bit, that's the thing that changes your consumption the most. And then the biggest variability relates to the country-specific electricity emissions factor. So in Sweden, it's extremely efficient to do video streaming. And actually changes in video quality have a minimal impact, which really surprised me because I assumed if you watched it in high HD, it would make a massive difference. Apparently, because the infrastructure's there, it doesn't really matter how much you send over it. Where it does matter is if you start pushing up the requirement for peak transmission, then you've got to increase the size of the infrastructure, and that does have an impact. Anyway, have a look at the Carbon Trust report because it's an excellent resource, and it also sets out all its assumptions and modelling very clearly. And then I've stuck up a few useful sources here, which I think people will be able to come back to. So that's the end of my part one. My part two, I would just want to look at a few myths relating to the data center sector. So I've talked about what I know, and now this is what I don't know really. So there are lots and lots of myths about data center energy use and ICT energy use generally, and I tend to lump them together because we all tend to be talked about in one thing. I think the Viking horned helmet is a great analogy. My favorite podcast is a podcast called Saga Thing, which is two sort of American academics talking through the Icelandic sagas. And the horned helmet has come up because the horned helmet, there's absolutely no evidence that any Vikings wore a horned helmet. It's a myth that was created in the 1870s, but the horned helmet is here to stay. And similarly, the idea of ICT using the same, emitting the same amount of carbon as airlines is also here to stay. So there are a number of these myths that just won't go away. And there's a great rule called Brandolini's law, which says that the amount of energy to refute a myth is 10 times the amount of energy needed to create it, which I think is great. I don't know whether that's true or not, but I thought it was a fun fact. Anyway, so we're going to have a look at a few myths and why they happen. I've put up a few sample myths, but I'm not going to read through these. It's just worth knowing there are a lot out there. I think the interesting one perhaps is that there's an interesting one about airlines, which we've debunked a long time ago, but it still keeps cropping up. And also we did see the Shift report claiming that 30 minutes of video streaming was equivalent to driving 4 miles or something. What's that, 6 kilometers? So there've been some quite outlandish ones. But I wanted really to talk about why we have myths. Oh, no, actually, before I go on, this is actually very close to what Simon said. This is to do with the different estimates you get when you're looking at data center energy use or ICT energy use. And this one is from streaming. And you can see an incredible variation in the estimates for the amount of energy that streaming consumes and the carbon impact of that. And Simon had that great chart with the different studies on data center energy use and how much variation there was. I'm going to come on to that, why that is. One of the reasons I want to start with was that there are multiple sources. And I put out this data center energy quiz to the sector and stakeholders within it. And I asked various questions. One was how many data centers are there in the UK? And the answers that came back varied from 105 to 180,000. So the ratio between, the variation was 1 to 1,000. There was 1,714-fold variation. Then I asked a boring question about meters of white space. Again, that was a smaller variation, I think perhaps because people had seen fewer figures on this. How much energy does the UK sector consume? I had figures between 2.4 terawatt hours to 320 terawatt hours. And since the entire UK's electricity consumption is only 330 terawatt hours, I thought the person who suggested 320 might have looked a bit more closely at some better sources. And then I asked them what was the average airspeed velocity of an unladen swallow. And since this is from Monty Python, which may not have spread into Europe, but it's a fictional UK program. There is only one source for this information, so everybody came back with the same answer. So what this told me was if there are lots of different sources with very varying numbers, people are going to have very, very different ideas, and there'll be no certainty about what the answers are. So my next slide is looking at why we tend to overstate data center energy demand. So firstly, and I know Simon's referred to some of these, so I'm really pleased to see that we're agreeing on this. The first one is old sources. Old sources are no good because ICT and data processing and all the technologies move so fast. Similarly, long horizons. There's no point looking too far ahead because, again, the same thing applies. ICT changes so rapidly. We've talked about the problem of definitions, and there are very different. There's no consistency in the way we define server rooms as opposed to data centers. There are definitions, but they're not consistent. Then there's the old making news. Everybody wants the biggest number to make news. Nobody is going to print something that says data centers consume a fair bit of electricity, but they're reasonably carbon productive. But they will print something that says data centers are going to consume all our energy and we're going to have to go and live in caves and eat bugs. Then we've got magic numbers. So we all look for some kind of magic number. We don't want the complexity. We want a number. And then once we've done it, we want to put that number up without any of the caveats or assumptions that are there. Then there's incomplete pictures. That means that what we're doing is we're creating a picture of the whole sector based on only one factor. So a classic one there is looking at growth in hyperscale and assume that growth applies to the whole sector when it may not apply to, we've seen what's happening to the traditional IT, but you can't apply it across. Then there's the old misinterpreting trends, and Jonathan Coomey does a great analysis of misinterpreting trends, which is much more technical than I'm going to go into here, but it's very easy to look at a trend and actually misinterpret how that's going to play out. Matryoshkas. This is because a lot of data center energy use, and the sector does this really badly itself, is we can count it twice. I have a data center can mean I'm inside someone else's data center, and when we ask them to report, they both report. So we try and get just the people who pay that energy bill directly to report. Now, the laziness one, rounding up the usual suspects. You don't bother to go down the first point in the Google search. So you just get whatever is top and most newsworthy, which doesn't assume that's true. Schoolboy errors, people mixing up watts with watt hours, and bits and bytes, which is why the shift report had to be revised down eightfold when it came out first. Then there's the extrapolations, and I know Simon's covered this, where you start with something and then you extrapolate. And again, Coomey has a great slide here where he says, oh, well, look, if you look back, you got married last week, you went from 0 weddings to 1 wedding. So if we extrapolate that up, you're going to have 486 husbands by the end of the month. So those are things where you've got to be really careful about your extrapolations. And then scenarios versus predictions. The Andres Andre figures were scenarios, and people have interpreted them as predictions. So we have to be able to untangle the difference between a scenario and a prediction. So I think those are my sources for myths. And obviously, I think there are ways that we can do better. As a sector, this has already been referred to, greater transparency in reporting. We're doing okay in the UK, but we don't have the full picture. Accept that nobody has the full picture. Recognise we're covering different things. Check when you're looking whether data is primary or quoted. Ensure the modeling's based on valid assumptions. Always check for agendas. People do have agendas. Compare lots of sources. And why not ask the people who actually measure that energy and pay the bills? And I know Simon is asking them, and I'm very happy to give him some responses. And if it looks ridiculous, it probably is. So that's my advice. And now I'm going to quickly move on to my part 3, which is what we're doing about this as a sector. And I just wanted to put this slide up because it shows that what we're trying to achieve, we're trying to reduce our carbon footprint to 2030 while having to handle a massively escalating demand for digital services, data processing. And again, this is a broader ICT picture, but you'll see data centers are featured within that. And we have to be part of that. I also wanted to talk about science-based targets. The ICT sector has released a science-based target, and there is a specific trajectory for data centers, which involves a 53% reduction in carbon. That's the grey line at the top of this chart. And as everyone knows, science-based targets, they translate global targets into corporate actions. operators are already signing up. It is a non-trivial activity, so we're asking the smaller operators to sign up to Race to Zero. And the reduction trajectory depends on us using 100% renewables. And actually, at the moment, over 90%, I think it's about 97% of the energy consumed by the commercial data center sector in the UK is certified renewable. But we actually want to move them on to approaches where they can create additional utility scale generation through things like power purchase agreements. Because, yes, if you're consuming from what's already available, you're not creating additional supply. So yes, a number of challenges. It's not going to be easy. We've got to get rid of our diesel generators. And actually, to be honest, I'd be delighted to get rid of them because they're the bane of my life. They create all kinds of compliance issues. So that's our science-based targets. And then I wanted to finish with the Climate Neutral Data Center Pact. And this, I'm absolutely delighted to be involved in this because, as Piers said, we have the same objective. We also want to see, resource-efficient data centers being the backbone for cloud services in Europe. We want to be carbon neutral by 2030. Sometimes when we have industry and policy coming together, we don't always agree on how we're going to get there. So I love the fact that we're having a proper grown-up conversation. We're agreeing how we're going to get there. We're agreeing what the priorities are going to be, and then they're working on it. And again, it's not going to be easy. But I'm really pleased that we're having this proper high-level conversation about it. I'll just quickly whiz through the various elements of it. So we're looking at, for instance, we're looking at energy efficiency to start with, and we will be developing a new metric. Developing performance metrics in data centers is fiendishly complicated. They're complex environments, and you have to take a systems approach. Because there's so many elements. If you make the environment, if you allow the environment to get hotter, then you've got to stop the server's own fans coming on and making the ICT less efficient. There's all kinds of balances like that. We're ensuring that the sector is entirely reliant on renewables. We want to minimize water use, and they're getting on quite well with the development for a metric for water use. It takes into account things like the different regional variations in water scarcity and the potability of the water being used. We're looking at circular economy for servers. That work's due to start, I think, in Q3. I'm keen to be involved in that, and also the reuse of heat. So it's quite a busy agenda, and I suspect we're going to have some quite interesting conversations going on. So that's, I think, the end of what I've got to say, and now I've got to work out how to stop sharing and hand back to Manuel in case there's any questions.
Thank you very much. My only issue with this morning, Eva, is that we don't get to enjoy to see the eyes of the audience, because I'm sure there is as a thrilled, and actually a very nice comment on the chat was about how skilled and delightful your conversation is. I need to confess, I had never thought that I would see a Viking helmet and a coffin on a data center presentation. So that was very, very unique. Let's do like with assignment. I'll shoot 5 questions, and I expect only a sentence or 2 in answer before we move to Jan. And they're a bit random, so they're hard to gather. So I will just shoot them. Emma, Elvis is asking, what is the percentage of data centers powered by renewables? We haven't talked much about it.
Okay, so commercial data centers, we've done it by the amount of power because we think that matters. So what we've done in the UK, I think I've just done a poll. I haven't got all the results in, but from the results I've had in, which represents 70% of the energy, 97% of that energy is certified renewable. But it varies by operator. So if I looked at all the operators, the way the sector's characterized is that there are many very large operators. So what they do is much more important than what the very small operators do. So that's why we do it by energy. But at the moment, from what's come back so far, 97% of the energy the UK commercial sector consumes is certified renewable.
Thank you. How do you feel? You've shown the International Energy Agency past figures, but there are as well provisions, forecasts for the coming 2 years, which are flat. How do you feel about that, and do you think it's reliable?
I think it's a great question. The answer is nobody has all the data. So my instinct is to nudge that line up a bit, but that's been really well researched. And I think the thing that we're often forgetting about is the existing very, very inefficient capacity on premises that's being dwindled away, outsourced. So we're not seeing that reduction visibly, but it's quietly happening in the background, and it does account for a lot. I think in the UK, we could probably save something like 2 terawatt hours a year if we sorted out that on-premise stuff. So these are big, big, big numbers in terms of what's there. But they're the, line with other people's figures. The line is relatively flat. If it nudges up a little bit, I wouldn't be surprised. So I would perhaps draw it somewhere between Simon's figures and the IEA figures, bearing in mind the IEA figures are global. So we're looking at slightly different things. And I'm sure we've used different parameters, different assumptions, and different models.
Thank you very much. Maciek is asking a question about experimental underwater data centers. I think Microsoft did one, but I would assume there's more in the industry. Is this the future of data centers? Is this the solution? Has it been tested? Are there scientific articles reporting on it?
This was Project Natick, I think, the Microsoft, and they lowered 2. One was off Orkney, and I forget where the other one was. I don't know in detail. I know that they've brought at least one of them up, and but I think the best place to look there is the Microsoft website, because I've seen reports on there about it, so I would have a look there. I'm not the best repository of information on that, but I'm happy to find you a link if that would help.
I remember the Microsoft blog posts about it, but I don't recall ever seeing an independent third-party analysis of it, which I think is going on.
Yeah.
Christopher is asking Emma, what is the single biggest challenge in keeping data centers sustainable? So a very broad question.
I think I will open it out and I say it's about transparency, but it's about ensuring that we all play a role. So I think I talked about the Jevons problem, that the cheaper it is, the more you do. So what we have to do as responsible consumers is understand that our internet activity has an energy impact. It might be small for each of us, but when you add that up, it becomes a lot. So I'd like to see us getting better information as consumers. And I think the business models at the moment don't help because they're freemium or advertorial, which don't provide that signal. Yes, if you're a business, you get a signal because you pay a charge. But when you're getting a service for free, you don't know whether uploading a video has a bigger energy impact than putting up a photo. So I think building that better awareness and understanding, I think, is the biggest challenge, so that we can all make informed choices. They may not be the right choices, but at least we're making informed choices. So I think that's it. It's this risk of proliferation because it's cheap and free, or free.
Thanks a lot. And the very final question, Emma, for which you're allowed to 3 sentences, because it's a part I'm not sure we've covered very much, and it's a true question in some areas, in some policy-making areas in Europe, is information to be provided to consumers. So really the end user, to the citizen. Should they be informed about the energy consumption? I mean, the question is on data centers, but maybe you can broaden this to the ICT sector. And if so, how and by who? And how can this work?
So yes, it's my answer. In one word, I only need one word, yes. But I think it's difficult. So we can, as data centers, tell everybody about our energy consumption. And in the UK, we do that, and we publish it, and it's public. And nobody seems very interested in it, but we do publish it. So that's one. But really, what you want to know as a consumer is the energy impact of your own consumption. And that is very, very hard to do on a per consumer, per consumption basis. And there's lots of very interesting initiatives happening. I think the streaming reports have been really useful, that actually as a consumer, you then can tell, well, okay, I can check out the credentials of my streaming provider. I can check out the credentials of my energy provider. Actually, since most of the burden of that seems to be actually which device I use it on, I can make those choices. So that is really important to know those things. It's important to know whether it's more energy efficient to transmit stuff over Wi-Fi, over fixed line, broadcast. Those things we all need to know. But once you get into the nitty-gritty, the sort of per transaction, it becomes fiendishly complicated because of the way that you've essentially disassociated the cloud service from the physical server that it's provided by. So that gets very complicated. But the short answer is, yes, the sector has a responsibility to do that. And also, in a sense, if we need to learn how we can best provide that in a way that's friendly and accessible for consumers, not with lots of charts and equations that with numbers that I don't understand. And I think that might be a role for policymakers to broker that kind of information. Bearing in mind, we do have a website, and I can paste up I think I've actually pasted it into the slides, where we provide a lot of information about the sector, but that's data center specific and it's UK specific, and it's about pulling that together in a consistent way across the whole of Europe. That's the tricky bit.
Emma, thank you very, very much. I think you're the professor I wish I had in my university time, so I'll give you my professor title as well. Thank you very much for your insights, smiles, and analogies, creative analogies. Thank you very much.
You're really welcome. You're very welcome. It's a pleasure.
It's time to welcome Yann Lechel. Yann is currently the CEO of Scaleway, which I'm sure he will introduce in more detail. But what you might not know is that Yann is a serial entrepreneur. So it's not his first time, and judging by the list of his previous investments and developments, he's doing this very successfully. Yann, I understand you're a professor as well yourself, as Dean said, so you already have the title. So up to you now to show us all about this. Yann, I think you're the one who's the most hands-on in the industry of this morning's speakers. So I think it's time to get more specific and concrete on how you see this question of the green data centers. Yann, over to you.
Thank you, Manuel. Clearly, I mean, my area of expertise in data centers actually materializes due to the fact that I pay the bills. So I actually know how much it costs, and the energy bill is the one thing that I look at because it is the biggest bill that I pay. And so for us, energy is a key indicator of our performance, our activity, but also a way for us to optimize at scale. So as you mentioned, I have a track record as an entrepreneur, but mostly in software. In other words, my main area of expertise is on the software part, which for the past 20 years as an entrepreneur has been using the cloud in a very distant way. And I joined Scaleway 15 months ago by discovering a jewel of a company hidden away, tucked away as part of a group called Iliad in France. And this cloud operator, Scaleway, has a very unique value proposition because we are an integrated player. So what I would like to talk about is the conundrum. And Emma talked a bit about that because we do have specialized value propositions in the market. On the data center side, for instance, you have large data center operators that are not cloud operators. And while we do talk about certain experimentations on the data center side here and there, and we mentioned Microsoft with a capsule that is immersed, Microsoft at scale is actually not deployed using those capsules. Similarly, if you look at the large hyperscalers, they are hosted by traditional data center operators. And so this notion of normalization is what I would like to discuss. I don't know if you can see my slides, Manuel. Yes? Okay.
Yes, can see them.
All right. So the issue, as we talk about the current moment, the snapshot picture, is linked to the fact that the current data center industry is largely specialized and built on legacy. In other words, we're talking about decades of cumulated capex deployed at scale globally on every continent, in every country. And these data centers are somewhat immutable. In other words, the machines within those data centers are filled with data, with processes for cloud operation. These data centers have been built decades ago, are meant to be operated for the next several decades, and these data centers are filled with racks and machines that need to be cooled at a 21 degrees average using air conditioning. And the industry is split between two players, and we know that the hyperscalers dominate the usage and the exploitation of these data centers, and you have specialized data centers operators that are also doing one thing, which is provide standard operations and standard colocation capacity. In the end, if you combine these three specialized tracks and the legacy, you end up with a weighted average PUE of 1.5, right? Which means that if you only look at the computing side of things, that's the 1 in the PUE. The 0.5 is wasted, if I take a shortcut, is wasted to cool the machines. So the efficiency of the overall cloud consumption worldwide is anchored due to the legacy and the sheer weight of the existing installed base. And I would like to contrast that with our experience as a cloud operator, but also as a data center operator, because we do both. We are one of the very rare, if not only, integrated data center and cloud operation provider into one, at that scale, that is. We are, in fact, a challenger because when we talk about hyperscalers, we talk about companies that are worth thousands of billions of dollars in the US mostly. Scaleway is not at that scale. We are a challenger, we're nimble, we're agile, but that is, in fact, our ability to do things different. And when we look at the energy bill, we need to try and find ways to optimize that. So our angle is largely driven by the need to innovate in order to compete because we are a challenger. And I will demonstrate that. Our weighted average is well below 1.5. And we, sorry, yes? No? So our current PUE is below 1.5 on average, well below 1.5 in fact. And the goal is to bring it down to 1.15, and I will elaborate on that. So just a few words about us. We're a company based in France. We are part of a group called Iliad, which is a telecom operator with a European footprint, 14,000 employees, and again, mostly an internet service provider and a mobile telephony operator, with some cloud infrastructure offering, Scaleway being one of them. International presence in France, Italy, Poland, Ireland, and others, with a very strong commitment for sustainability to reach ambitious goals by 2035. Now, Scaleway is a fully owned subsidiary of the Iliad Group, also based in Paris. And we are not a telecom operator, we are a cloud operator. And so we have combined revenues of 82 million euros in 2020, combining cloud and data center revenues. And our overall capacity under management is 20 megawatts. That's about 10,000 racks in production, 4 data centers in Paris, or around Paris in the near side belt, and 2 other data centers in Europe. We are also co-hosting our biggest competitors. So we do have our competitors within our midst in our data centers. This tells you the quality of operations that we are able to provide, because as you can imagine, hyperscalers are extremely demanding. We have sustainability goals, which are to reduce power consumption by over 40% by 2025. So the energy aspect of things is critical to us. And one of our latest data centers is in fact already near carbon zero. But this is a goal that we're trying to achieve by 2025, 15 years ahead of the Paris Climate Accord, to have zero direct carbon emission overall. And of course, we'll take that goal further by 2050. Now, I will not go into details on this slide, but this is the history of our data centers at Scaleway. Spans from 1999 to 2020, And we've gone through all the iterations, and we have older data centers and newer data centers. Now, what makes us special here, and the reason why I would like to elaborate on the right side of the picture, is that we have our own skin in the game. In other words, we are majority hosted in our own data centers. So we know the direct impact, and we have the ability to change things. We are vertically integrated, and by that I mean that we operate the data center, we purchase the hardware, we fill in the data centers, and we also develop the software on top of it. So we are, in fact, more of a software company than a data center operator, because creating a cloud stack is extremely, extremely competitive and complicated. Now, over the past 5 years, we've become the most successful colocation provider in France as a French company, because most of the players in this field are very large real estate companies that specialize in data centers. And most of them are not French. They are international or American. Now, let me zoom in on this picture to give you some concrete numbers. And I hope this converges with the numbers that Emma has seen over the market. So traditional data centers, and I'm not talking about the newest generation, I'm talking about the average traditional data centers that are deployed worldwide, generate 74, and it uses a lot of air conditioning, and only 70% of the energy is available to compute. Now, on the right part, this is our latest cutting edge data center, which is representing more and more of our facilities and operations. Now, the CO2 generation is drastically reduced. The water consumption is close to nil, and the power usage efficiency is 1.15. How is that possible? Well, I just want to be very clear. And Emma talked about making sure that we are educating the market about energy. Now, we are fully transparent. This is a picture that is available on our website that explains which data center has which PUE. Now, not all of these data centers have the same energy available. They're not the same size. Some of them use older technology. Some of the new ones, DC5 is our largest site yet, and we are largely positioned in this one. So this is our biggest in terms of operation, but very quickly eclipsed by this one. So this means that the center of gravity and the weighted average will be oriented towards this data center that will represent at the end, once we fill it in, 22 megawatts of power. So that data center is actually quite unique in its design because it uses adiabatic cooling. We do not use air conditioning in this data center. There is only one air conditioning unit for the humans in their operator room. There is no air conditioning at all for the machines. We use a giant airflow to take the hot air that is coming outside of the fans of the computers and push it outside. How do we do that? We generate an air tunnel using pure water evaporation to create an air draft. This is called the adiabatic cooling principle. It's as old as 3,000 years old, used by the Egyptians to cool off their food in the jars by using wet towels. And we've been able to do this, as I said, because we're nimble, we're agile. We have this ability to innovate for ourselves. And to be frank, I'm sitting next to the founder at Scaleway, who's the one who invented and who dared to invent this process and deploy it at scale. That was 3 years ago. And 3 years ago, people thought that this was nuts, right? How can you possibly use water to cool the air and to actually send a massive airflow through the computers? Because you fear corrosion. You fear that this is going to be too humid. Well, no. In fact, when you do this properly, with proper engineering techniques, with proper testing, with thousands of sensors throughout the data center to modulate every parameter, then you end up with a data center that so far has been operating 10 seasons, 10 Parisian seasons, and 3 heat waves. And this data center, I'm telling you, has not had a blip in operation. In fact, this data center operates better than our other more traditional data centers that use air conditioning, because once there is a heat wave, we need to cope with a sudden increase in resources to cool off even better. And in some cases in the US, they use a lot of water, which is something which is highly regulated in France. So using more water is not the answer. DC5, as I said, uses adiabatic cooling and direct free cooling. And this cooling uses just a little bit of water, really just a little bit, to create this air draft. So as you can see, we also include the WUE, which is the water usage efficiency, which is very, very small. So again, we're very proud of this data center, and we have skin in the game. We use it for our own, and we have dozens of millions of euros of computers in this data center, and these computers are perfectly cooled. In fact, I will tell you a secret. These computers are not cooled at 21 degrees. They're cooled at 30 degrees, which is perfectly fine. What computers do not like is temperature variation. And we're providing the perfect environment at 30 degrees that produces no more destruction than any other data center. So 30 degrees is actually just fine. To increase and to participate in the conversation, we are going to be transparent to the point of publishing this indicator, which is a very simple formula. I'll spare you the math, but the PUE is the power usage efficiency of a data center. But for a cloud operator, and as we discussed earlier, typically, and Emma mentioned this, a cloud operator has information to the tune of what the data center operator is telling them. Well, for us, we know those numbers specifically per rack. We know how much each rack consumes in each data center that we operate. So what we're doing is we're creating a weighted average PUE for our cloud operation. In other words, we're not taking it from the data center standpoint, we're taking it from the overall cloud operation. So as a software consumer, you know exactly the average PUE of your infrastructure as a service. So we've got the EPUE, and we do the same for the WUE. We've got the effective water user efficiency across all of our data centers. And we just take the average of these two. So for us, the current EPUE is 1.37, as I said, well below 1.5. And the water usage efficiency is, on average, weighted average, 0.01. So this indicator is our own. We've decided to come up with this indicator. Why? Because we want to publish it every year and show and tell our clients that we are improving our operations. Because our clients are cloud clients. They are looking for software and service to build their application, be it a health application, be it a banking application, be it entertainment, streaming, or video sharing, or picture sharing, whatever. So the EPUE is at 1.37 at scale weight today, and it will be converging to 1.15 because our next data center and the one after that one will probably strive to even improve that number. Currently, we know that if we fill in DC5, which represents up to 22 megawatts of energy consumption, we will largely converge towards 1.15. And therefore, the RDCE will be converging to 0.58. And we think this is massive gain for the end client. So DC5, this is the empty room. A data center is nothing more than a cool room. But in our case, we do not use air conditioning, as you can see. An empty room is ready for an airflow that comes from the outside, where I'm sitting at and looking at this picture, and then we'll stream back up in the middle ceiling, as you can see there. DC5 is located northwest of Paris. That's a 40 minutes drive. and the benefits are immense. It's very radical as a design, in fact, what really matters is the ultra low PUE of 1.15. We need to also point out that the PUE in Europe is strictly computed. In our case, it's 1.15 for the data center, including the energy consumed by human operators. In the US, they tend to use a PUE that excludes human operations. So they get better PUE, whereas in Europe, we get penalized because the law is strict, which is fine. We need to have those conversations. So in a nutshell, this is how we're doing things. I'm not talking at all about the software, which is even more complex, but is fully a part of the equation for us, because we do believe in a cloud that makes sense. In fact, this is our tagline. Scaleway is fully invested to answer all of the hard questions, because energy consumption is part of the equation, but also want to reassure the audience, and that was mentioned earlier by Emma as well. There is a lot of computing out there in non-optimized racks. So even though a data center consumes a lot of energy, some more than others, a data center is operated by an industrial player. And industrial players, they do optimize their costs. So we can look at these racks here, neatly organized. Every inch, every watt is optimized as much as we can. But it's the weighted average of the overall operation that will make a difference. So this is it for my presentation. Manuel, if you have questions for me, I'd be happy to answer them.
I do. Thank you very much, Ian. Very insightful and indeed an excellent complement to what we've heard before, much more detailed and hands-on, and we indeed feel the fact that you're the one paying the bill at the end, as you said. And I need to say that after the coffin and the Viking helmet, the analogy with the Egyptians was as well another reminder that this is not all completely new. A few questions for you, Jan. We still have 20-25 minutes to go, and then I'll open up a broader question that we've not touched back with Simon and Emma as well. But first with you, Jan. You've presented quite a few innovation or research and innovation new features. What do you see moving forward? What are the next steps in research and innovation? What are the new things that can further improve what you're doing? It's a question from Gordon.
Okay, thank you, Gordon. Well, clearly, I mean, the holy grail is a PUE of 1.0 in terms of data center operation. But that only assumes a perfect system and excludes all of the software optimization that we could imagine. But that is only possible if there's a fusion between the data center operation and the software operator over the top. So we've heard things about Google using DeepMind to optimize certain things, but that is not something that I'm competent to talk about, because I do not know how far they've gone to integrate the software layer of the cloud operator. In other words, the hypervisors and the storage component of the cloud service with the actual data center. In other words, we need to think about the perfect equation. How much computing is required for which energy, for which problem, and at which time? And this convergence currently is not occurring because we do have the data center and cloud conundrum that I talked about, because we have specialized players. So a cloud operator that only does colocation is completely unable to provide the proper links to the upper level of the stack. So Scaleway is very much integrated, but that we are a small player. So there's so much we can do to impact the planet, because the planet is currently impacted by all of the players, including the massive ones. So we're going to see gains at the specialization level. So perhaps there is an ultimate PUE of 1.0, but to go beyond that, we need to look at power efficiency from the chip design all the way down to the speed clock. In other words, can we modulate the clock of the CPU based on the type of computation that is required and at which time? Currently, there is no such integration between the data center and the speed clock. Scaleway was, for instance, a pioneer in bare metal using the ARM chip design. So ARM processors, which were invented in the UK, are what power most of the cell phones today, smartphones. And back in 2013, I was not at Scaleway, but Scaleway invented bare metal as a service using ARM because the energy consumption was out of this world, typically 10 to 20 times less than a usual Intel AMD rig. Now, the problem is ARM processors have been built and exploited for smartphones, but when we talk about the cloud, we're looking for backend, we're looking for Linux distributions, we're looking for databases, we're looking for softwares for the backend. And the ecosystem for ARM processor and operating systems on top of that was not well developed back then. There's going to be a resurgence of that, and we're seeing some positive signs. So the chip design and the ecosystem around the chip design is paramount to developing new, more optimized models. So in a nutshell, what I'm saying is that we're going to need to see convergence of multiple streams that involve both energy efficiency data centers, airflow designs, perhaps different locations on Earth, right? We know that data centers in Northern Europe fare better and are easier to cool off because it's colder, simply put. It turns out that our adiabatic cooling system would work perfectly well in the Middle East because there is low humidity and a lot of sustainable heat. So we can create energy transfer by using a little bit of water. Again, these things are complex systems. The way data centers and hyperscalers are designed, I think, is a problem long term. And part of the solution, in fact, involves edge computing as well. But edge computing is a software problem. Once we atomize and change the granularity of the hubs and the data center, then it becomes a software problem.
Okay.
Convergence.
Thank you very much, Jan. Let me try now to combine two questions from the audience about the reuse of weight. Romain is asking, I think, in a broad sense, whether instead of focusing on reducing the consumption, it wouldn't make sense to, or wouldn't it be easier to reuse the generated heat rather than focusing on reducing it? And something to which Vlad says, what about expanding the boundaries of reuse? And he puts the question, wouldn't it be better, what is best, data center in very northern Europe with a PUE of 1.1, or something much more centric? He gives the example of Frankfurt with a PUE of 1.3, so not as great, but where the heat goes into district heating. So I think the question is, what is the role of heat reuse, and how much can it play a role into the overall equation? So
I'm terrible in thermodynamics, but one thing I've understood is that the heat generated by a data center, and I was visiting DC5 just this weekend again, because we bring people to visit it. It's quite stunning. When you're sitting in the back of the data center, literally, the air is coming out, right? But it's coming out at a 40, 45 degrees temperature, and then mixing up with the general air. Now, it's not bad, but it's hot, but not so hot. In other words, to reuse that energy and transport it, to reuse that heat, it will need to be compressed at massively higher temperatures. So that's not something we can do with a data center that is in the middle of nowhere. Now, I think what's going to happen, and we can look at the history of computing from a compute standpoint. We've gone from centralized to decentralized, centralized to decentralized. If you look at a smartphone today, smartphone is massively more powerful than the mainframes of 50 to 70 years ago, clearly. So there's been a ping pong because it's the hardware that evolves to the point of being not sufficient, and then the edge component picks up the load. Remember the PCs were pretty powerful computers for the homes, but were perfectly deconnected. Then they became connected, and we had thick clients, and then thin clients again, back and forth. Now, if you look at this ping pong between client and server, you are likely to see it again with the edge evolution. Now, edge computing will transfer part of the heat generation to the edge. And the edge computing paradigm is actually useful for one thing, because you said, what if we put the data centers there or there? Now, if the data centers are far from the consumer, you are taking in milliseconds delays that are not wanted for real-time operations. If you think, if we project ourselves into augmented reality, we will need super responsive computing, right, on the edge as well as in the cloud side of things. So what edge computing requires is 5 milliseconds between the consumer, the antenna, and the edge component. This cannot be achieved with the current massive data center approach, where typically we take 100 to 200 milliseconds to do the round trip calculation. So let's assume that edge computing will be a design that actually is capable of bringing more value and shorter latency with the consumers. Then we can assume also that the edge design will carry a little bit of the heat generation to the edge as well, where it will be closer to the consumers. I have in mind a company, a French company also, called Carnot, and they build heaters with a CPU inside. So they're providing the CPU as shared resources in a grid, but it's a heater. In other words, you are getting the heater, not the computer, right?
And Carnot is certainly a good name for
exactly.
Such
so it's the early days of the edge computing, right? But this is precisely the sort of optimized model where someone who lives in a continental climate or somewhere where you do need heaters, so someone we mentioned Belgium, France certainly, UK as well. We could all use some more heat during the winter. Then computed heaters could do the trick, but they have to be part of a huge matrix, a huge mesh called cloud to edge computing.
Thanks a lot, Jan. We understand the equation is not that simple. 3 very tiny answers to 3 questions, and then I want to open up back to Simon and Emma on the question of electronic waste. 3 questions. Jan, the role of distributed protocols, such as the butterfly protocol, distributed blockchain, not a Bitcoin, which is maybe a specific case, but let's speak about distributed protocols. Does it matter? Is it important for you? Quick one.
Yes, and we monitor very closely some of them. Some activities are not possible in industrial data centers because we have a shared infrastructure, and some neighbors are not welcome because we do not control their spikes. So typically, mining is complicated. Now, there is one that came out recently called Shia Network, and they do proof of space and proof of time as opposed to proof of work or proof of stake. And this is an amazing innovation because they use resources very well, except for the first part, which is called plotting. And plotting actually is really bad for our current hard drives. It destroys them. So the pricing should be adapted But yes, we are looking at Web 3.0 infrastructure because these distributed systems are extremely intense, and all we need to do is shape up the equation to allow for them, because they do provide value to the economy as well.
Okay, thank you. Echoing a famous case of fire in a data center, which was not Scaleways earlier this year, there's a question from Maciek who asks whether fire risks are taken into account when deciding of the location of a new data center. Is this something you take into account?
Yes and no, because a data center is just a warehouse. And what happens inside is that you have a lot of energy, you have batteries as well, and you have computers. So fires occur in data center from time to time. But for a complete data center to be carbonized does not occur. It's a very unfortunate event that occurred there in Strasbourg. Our data centers are not built that way. It turns out that cloud operator has its own design for its own data centers, for its own computers. So they are not standard in a sense of co-location. Our data centers are standard in the sense that we can bring any sort of standard rack into the data centers. And as you can see in the picture, actually none intended for this question, but we do have a real fire extinguisher right there. But actually, you're not seeing the picture I'm saying. I disconnected my presentation. Anyways, our data centers are fireproof. We have the certificates posted on our website. We take extreme precautions. And as I said, we have one of the most demanding cloud operator in our data centers, and they expect the very best protection. Operating a data center, especially on behalf of others who have put inside the data center millions, tens of millions, hundreds of millions of euros worth of hardware, is a risk management business. And we take this very seriously. So whatever happens, data centers do not burn. They do not. They just simply do not.
Thank you very much. Thanks a lot, Jan. I've kept for the end an interesting question that popped up earlier, and I kept it now to the end, which is about electronic waste, because the session of the university of this afternoon, starting at 2 p.m., is precisely on electronic waste and circular electronics, and obviously data centers are a big consumer of electronics. So I'd like to reopen briefly the panel for the last 10 minutes to this question. Let me start in the order of appearance. Simon, you presented to us questions on energy consumption, but we understand this is really the operation of the data center. Do you factor, or how can we factor what is sometimes called the embedded electricity? So all the energy that has been gone into the production of the materials that reach the data center. Do you look into this as well?
Yeah, we try to collect data on these different topics, on these different steps of the whole life cycle, if you want so, like the production, the transportation, and also the assembly and recycling of materials. But it's really hard to get detailed data on these manufacturing processes, because on the one hand, there are some data available, but this is often like 10 to 15 years old in these inventories, in these data inventories, and the processes are changing too fast that we could still use these data that is available. Like you could, for example, calculate with the chip surface, you have a chip that size, consumes that energy in production, but that could have changed at a scale of like 2 or 5, because the production, the type of production has just changed. And with the ICT, you have this changing rapidly, so it's very hard. But we've made some estimations on that, and we still have calculated that more than 80% of greenhouse gas emissions and about 90% of electricity consumption, if you look at this in like Germany and the typical production countries, like more than 80% of greenhouse gas emission and 90% of electricity is happening during the use phase. So the production phase is a very small part, but it's for data center equipment, for end user equipment like smartphones or computers, it's different. There is the share of production much higher. So there is a different situation. You cannot compare this, but that's definitely an issue, yeah, to calculate also, or to at least be aware that this is one thing. But a second thing to this, just a quick thing, is that the usage lifespan of ICT equipment in data centers has increased. The Uptime Institute does data center studies with many data center operators, and they have found that in 2015 the refresh cycle for servers was still 3 years. Now we are in 2020, we have seen a refresh cycle of 5 years. So as the improvement of performance is getting a bit slower, the operators tend to keep their hardware longer in operation until they change it and refresh the equipment.
Very interesting, Simon. The comparison in between the end devices and the data centers, the scale is different, and the equation of waste of embedded electricity versus operational electricity changes, and then the lifetime of servers. Let me turn to Emma. Emma, what is the broad industry perspective on this? Are there initiatives? I mean, in the EU, we have the WE directive, which frames all this, which I suspect the United Kingdom is still somehow following. But what are the figures there? What is the industry doing?
So figures I'm not very good on, but I can tell you what the industry is doing. But they're doing different things in different parts. So if you look at the hyperscalers, they tend to have rapid server refresh, but closed loop systems. So you're not actually replacing the whole server. You're putting in a different processor, or you're fiddling around with the existing server. So you're not taking out a server and replacing it with a new one. And they tend to have these, as I said, closed loop systems. There's some great reports from some of them on that. The other sort of, I suppose, business model level development is that we're starting to see the provision of servers as a service. So rather than manufacturing and selling, we're starting to see some of the big server manufacturers provide those servers as that's a terrible thing to say in one sentence, servers as a service, which means they get it back. So you have a more closed loop. What's interesting to me is the really difficult balance, which Simon alluded to, is between the refresh cycles when you're trying to optimize energy and when you're trying to cover wider sustainability impacts. So a refresh cycle for a server will be shorter if you're just looking at energy, but needs to be longer when you're taking into account a multitude of other sustainability factors. And there's some very good third-party academic reports on that if anyone needs that, just how you balance those, and also balancing the uncertain and unknown factors. I think the other thing that we need, we are looking at, and is happening actively but on a more informal level, is just to ensure that we exploit all the potential for reuse. And if you take what we call an end of, a first generation server or a recent server, it has fantastic capabilities for reuse in others, where it will save energy and it will save money, because there are plenty of data center environments, particularly on premises in enterprise, where the servers are old and therefore they're relatively very inefficient. The biggest issue I think we've got, which is really my concern, is that what we're trying to do is ensure that used servers can get to refurbishers and be refurbished, but being aware of how we handle the number of bad actors who exist in the waste stream. And that's true of all waste streams, but particularly e-waste. How do we deal with moving waste streams around without making them vulnerable to bad actors? And that's a mixture of industry and policy. So I think that's a big concern going forward, to how we deal with that. And it is, I mean, I'm sure you agree with me, it's not easy. So I think those are my thoughts on it. But I'm sorry if that's a bit rambling. I haven't given you any useful figures at all.
No, that's interesting, Emma. Thank you very much. Jan, to finish with you on this question, you pay the bill for the electricity, but you pay the bill for the service as well. So I imagine you try to improve your return, your ratio there. What is your policy on purchasing and then the end life cycle of your servers?
It's a complex equation as well, and of course we look at it very carefully. We do have a mixed offering which allows us to play with those variables a lot. We do have a bare metal offering where clients rent the whole server, and we do have the hyperscale elastic version of that as well, where clients will rent by the hour fractions of a server. Same for memory and for storage. But we do have one goal, which to extend and recycle the hardware life from 6 to 10, right? 10 years, which is significant. So as Emma said again, this is closing the loop on these components, making sure that we're not wasting additional resources that are being paid for, but have generated a lot of e-waste, if you wish. So we do work on that actively because it lowers our capex, and that is key. And then we do also study the equation, which is based on the supply and demand of the market. In other words, what are clients looking for? If you look at, for instance, GPU computing, AI demand, we are still very early in that race, and the models, if you look at the latest linguistic models that have been published by OpenAI, they are massive. And so the demand for these models create demand for much more recent hardware. And that equation is complex because if you do not own the data centers and operate those GPUs in a data center that is energy efficient, then the price equation of the hardware collides with the OPEX, which is the cost to operate that blade. So it's a very complex equation, and we need to look at that per operator. In our case, we look at it from our standpoint, and we also look at it from a use case perspective. In other words, again, there is no simple answer, only to say that industrials optimize everything all the time. That is the one thing that we do, and regulators can help to actually set ambitious goals. And I think Europe is well attuned to the possibilities, and Scaleway is very happy to oblige to the most stringent of the regulations, because we are at that level of expectations for ourselves.
Thank you very much, Jan. I take that being a manager today is equation intensive as much as energy intensive. So thank you very much to you, and thank you to the board of professors of this morning's university session. I think it was extremely interesting for me as well. And I take from the chat that the 400 people who been listening and collecting the stamps for their Connect University diploma have enjoyed the session very much. Thank you again. It's 12:02, so we kept the time. The next session will be at 2, and we'll focus on minimizing e-waste and all the aspects of circular electronics. So this was an excellent transition, first for lunch and then for this afternoon session. Bye-bye, Europe, and see you very soon.
Thank you.